we're going to do a quick example from 8.2. And before I do that, Kavita wants a nice little shout out. So this is shout out to Kavita. And with this, we have to, part A is get the vector and the parametric equations using the notation that I just showed you from the text. So the first part to the equation is always x comma y comma z. And then you need any position vector, which can come from this point, which is given. Then the next part you need is any two vectors, any two direction vectors, which are on the plane. And you were given that A and B are on the plane. So then we just go plus t times the one vector and plus s times the other. The t and the s, they don't really matter. You could use any letters. We'll just stay consistent with the textbook. So we're just going to take all the components for the parametric. So you take all the x components, which is x, and then we have a 6 plus 1t, and then plus 8s. So there's the first one. Y equals 0, and then plus 4t minus 3s. And our z would be 1 minus 2t minus 2s. So that's just subbing in our Q point into our parametric equation. So we're just going to take our first two, I'll call it 1 and 2, and I'm going to substitute this first one into the second one to be able to solve for s and t. So now that we have that s, what do we do with the s? Good, we can sub it back into the first one. So our t equals negative 11 minus 8, and then times the 46 over negative 35, and our t ends up being negative 17 over 35. So we're going to take and we're going to put into 3 these values. So our left side is 6, our right side is 1 minus 2, and our t is negative 17 over 35 minus 2, and our s is 46 over negative 35. So now that you have 18 over 5 on the right side and 6 on the left side, is this point Q on our plane? No. Our left side would have to be right side, equal each other in order for the point to exist on that plane. So we just picked t equals 2 and s equals 3. It can be whatever you want. It could be t equals 1 and s equals 1. You get to pick. And if you keep simplifying and you add all the terms together, you end up this. The last question is asking about an x-intercept. How did we previously find x-intercepts before? 0. So if we're going to find the x-intercept, we have to let y equal to 0, and our z also has to equal 0 in order to find just where it's touching on the x-axis. So after you've done the substitution and elimination and you found your s and t, you need to take those values and you need to sub it back into your original, because we haven't actually said the x-intercept yet. So your x-intercept is 17 over 2. And if you were to say it as a ordered pair, as a point, it's going to be 17 over 2, 0, 0. Okay, so in 8.3, we're going to look at scalar, which is a few more properties of finding equations for the planes. And just like before, the coefficients from the scalar equation are the coordinates of the normal vector. The normal is the perpendicular vector. So if you have that plane, wherever your plane is on the axis, that normal is the perpendicular vector to it. There are 3 different ways that we can solve for the scalar equation, and it's the dot product, using the actual formula, and then using 3 points. So the first method is using the dot product. What do we know about the dot product when it equals 0? What do we know about those two vectors? It's orthogonal or it's perpendicular. So if we can find a perpendicular vector, that will help us to find this equation. So if we have PQ, would we be able to find that vector based on these 2 points? If we made up Q equals x, y, z, we're just going to call it x, y, z. Can we find that vector? So this is going to be a vector which is on our plane. We are also given the normal, which is 3, 1, negative 2. So if this is on our plane and this is normal, what should happen when we take the dot product? It should be 0 because this normal is perpendicular. Good. So let's do that. So once you've taken the dot product this far, we also said that these two were going to be perpendicular. So this dot product should equal 0. But we can simplify this a little bit. We can go 3x plus y minus 2z, and we can simplify this to plus 16. And what do you notice about this equation? It's scalar. So if you're going to use the actual formula, we were given the normal. We were given that the normal is 3, 1, negative 2. And if you remember back to the equation, ax plus by plus cz plus d equals 0, what did we know about a, b, and c? So if we're given the normal, which we are, which was 3x plus 1y minus 2z plus d, we can just put in those coefficients into the a, b, c spots. We were also given one other piece of information, and that was the point P. What can we do with that point P? Perfect. We're going to sub it in for x, y, z. What's going to be the only variable left? D, and you'll solve. So you should end up with the same equations once you're done and you solve for D and you substitute it in. You have used these 3 points, turned them into vectors, taken the cross product, which gets you the normal. Well, you're back to the question you were before. You now have the normal and you have points from before. So you work with that normal and one other point, and it will become a question exactly like this. So from method 3, once you have all that information, you would go back to method 1 or 2. You would use the normal and the dot product, or use the normal and the point with the formula to solve it the rest of the way.